Well, good morning everyone, and welcome to the Biotransport class at the University of Toledo. Today we start lecture number 3, and I'm down here once again in the COVID bunker. I hope everything's going well with you guys during your first week. Hope you had a good weekend, and yep, starting to get a lot of homework zeros in, so it looks like you guys are pretty familiar with MATLAB, so I don't see any issues there. So what we'll do is continue on in talking about stuff in chapter 3. Last time we started talking about the fluids in the body and capillaries and things like that, and that also led us then to the idea of osmotic pressure, and we went through some thermodynamics back in chapter 2 and came up with what's known as Van Hoff's law, which allows us to calculate the osmotic pressure if we know the solute retention. It's important to remember that it's only the solutes that are retained by the membrane that generate the osmotic pressure. So if a molecule can freely go across the membrane, that doesn't generate any osmotic pressure. And we'll be getting more into that in today's lecture. Also, we'll develop today the expression for the filtration flow across a membrane. Remember, I was telling you guys the other day that the flow of anything is proportional to a driving force divided by a resistance. And in this case, the driving force we'll see is really the effective pressure drop across the membrane, which is made up of both the hydrodynamic pressure that exists across the membrane, as well as any osmotic pressure differences that exist across the membrane. So that's all I got here. Let's get started with the lecture then. Okay, last time we went through some thermodynamic arguments, which is shown above here on page 79, and that led to the boxed equation, which is known as Van Hoff's law, which allows us to calculate the osmotic pressure in terms of the solute concentration. So if you know the solute concentration, you can calculate the osmotic pressure. And remember, we're going to be using a capital pi sign for osmotic pressure. That's your gas constant, temperature in absolute units. And then you just have to choose the appropriate gas constant to make sure that you get the units all worked out there. And this is what's valid for what we call ideal solutions, and for the most part biological solutions to a good approximation. We can use this equation to estimate the osmotic pressure. Now you're probably wondering, well, hey, we developed this basically for a binary solution. We just had a solute in water. What if I have a variety of solutes in water? How do I handle that? And what do I do with things like sodium chloride, which are strong electrolytes? When you put a strong electrolyte into water, it'll instantly ionize and form sodium ions and chloride ions, and it's important to remember that each of those ions will contribute to the osmotic pressure. So in a multi-component system, each entity contributes to the osmotic pressure, and it's important that when you do these calculations to carefully look at the nature of the solute in terms of whether or not it's going to ionize or not. So what's going to happen with Van Hoff's law, just like with ideal gases? In fact, this equation looks a lot like the ideal gas expression. Concentration is just moles over volume. So if you brought the volume over here, it would be a pressure times volume equals nRT. So it's an amazing coincidence, and it has nothing to do, and we're not saying that solutes in a solution behave the same as molecules in the gas phase. It's just an incredible coincidence that Van Hoff's law has the same form as the ideal gas law. So that's kind of amazing. But what's going to happen then is each entity itself will contribute to the osmotic pressure. So we can calculate the osmotic pressure contribution of each entity and then just sum over all of the entities to get the total osmotic pressure. R and T would be constant, and that's what we show on the next page here. If I flip this page over, we get the equation that's shown up here at the top, which is the equation we use. This is the equation you would use if you have a multi-component solution. So you just sum over all the entities. And usually, you got to be careful. Like if a problem says you got a 1 molar solution of sodium chloride, that means that you've really got a mole of sodium chloride and a mole of chloride. If you don't make that distinction, then your answers are going to be off, say, with sodium chloride by a factor of 2. So when I'm working these problems, I always break the entities down, say, into sodium and chloride, figure out what the concentrations of each of those ions are, and then just sum over all of the entities. I think that's an easier way to do that. So let's just look at an example so we can see how the numbers roll through something like this. So what we got here in this problem is it says, consider the situation shown in figure 2.5, where on side A of the membrane we have a solution that has a water mole fraction of 0.99. On side B of the membrane we have pure water. Temperature is 25 degrees C. Estimate the pressure drop needed across the membrane, that is PA minus PB, to stop the osmosis of water from region B. Okay, so what we're doing here is I just made a drawing now right down where the action is in that U-tube. Here's the membrane, and I've labeled side A, which has the solute. That's what the black dots are. Side B is just pure water, and Q is the filtration flow. So if the pressure on what's going to happen here is that normally, like when we set up our little thought experiment, the atmospheric pressures, the hydrodynamic pressures on each side were the same, and the water flowed to the left by osmosis, water diffusing from high concentration to low concentration, and then the level over here rose until you had enough hydrostatic pressure to stop the flow. Now in this case, what we want to do, as the water goes across the membrane by osmosis, we want to figure out what pressure do we need on the A side in order to stop that flow. Okay, and generally what we can do is, if we're thinking about flow across the membrane, we can write this equation right here. This is going to be equation 3.4, which I'll point out in a little bit, but this is called Starling's equation. And basically it says that the filtration flow across a perm-selective membrane is given by the driving forces, which would be PA minus PB. That's the hydrodynamic pressure difference. And our intuition would tell us that the pressure is higher over here than it is over here, the flow is going to go to the right, and Q would have a positive sign. Now one of the things you have to be aware of in transport is you got to pay attention to the sign sense. If the signs would flip, if Q would come out to be negative, that would just mean that the flow is going in the opposite direction. Now for sake of argument, if side B was just pure water, then its osmotic pressure would be 0. On the other hand, side A has an osmotic pressure of pi sub A, and we could calculate it by Van Hoff's law. So if we have a real high pressure on this side of the membrane, which is forcing the water to filter to the right due to this pressure difference, if we have a retained solute over here on side A, that's going to generate an osmotic pressure, which is going to cause a back diffusion of the water. So that's why we have the minus sign here. So this would be minus pi A. And then if we did have osmotic pressure, say a lower osmotic pressure on the B side, then we would subtract off a B from the osmotic pressure of A, because that just decreases the driving force. So what this bracketed term represents then is the effective pressure drop across a membrane when you have a retained solute. Now remember I told you that the flow of anything is proportional to a driving force divided by a resistance. Well, the inverse of a resistance is a conductance, and it just works out that in membrane technology, rather than talking about the resistance of the membrane, we work with what's called the conductance. And the conductance is separated into two parts. If you think about the membrane here, everything being equal, you got the same driving force, and you've got the same internal resistance of the membrane to the flow. then you would know by intuition that as you increase the surface area of the membrane, the cross-sectional surface area of the membrane perpendicular to the flow, you should get a higher volumetric flow rate. So that's why they separate in this conductance term, the actual surface area of the membrane, because you as the engineer, that's one of your degrees of freedom in terms of whatever it is you're designing. And L sub P is called the hydraulic conductance, and hydraulic conductance is independent of the surface area of the membrane, but depends on the nature of the fluid itself and the internal porous properties of the membrane. And later in today's lecture, or maybe the next lecture, we'll be delving into a deeper mathematical understanding of what LP happens to be. But in any case, in terms of this example, what we want to do is we want to find out the pressure drop needed across this membrane to stop the filtration flow of any water across the membrane. Well, that's going to happen when Q is equal to 0. There's no bulk flow. So that means these two parenthetical terms would have to equal one another. We already know on side B we have pure water. So we're left with the result then that the osmotic pressure is equal to the pressure difference across the membrane when the flow stops. So that's what's illustrated then in the calculation right here. You can see the osmotic pressure is equal to the difference in pressure across the membrane, and we can then calculate that. Let's see, assuming the solution, okay, ideal solution, we can use equation 2147 to calculate the osmotic pressure of region A. So what we have to do then, in order to find the required pressure drop PA minus PB, we're going to have to calculate the osmotic pressure of the solution on the A side. And that's what's shown here. We're just using equation 2147. Notice the dimensional equation where every number you write down has units on it. It's very important that when you're doing engineering calculations that you use the dimensional equation approach. So these are all, this is the gas constant, temperature, some units conversions to get from Pascal to atmospheres. This down here is the molar density or the molar volume of water, and there's the mole fraction. So we end up with a pressure difference of 13.6 atmospheres across the membrane in order to stop the flow. Another example is shown on the next page where we can actually calculate the molecular weight. So imagine you have a solution, say with a protein in it. You've created some new protein or you got some new antibody, and you want to calculate the molecular weight of that macromolecule. You can use equation 2147 and rearrange that equation as I show here in equation 2149 and solve for the molecular weight. And what we've done right here is we have the mass concentration. So little m solute would be the mass concentration. That would be like how many grams per liter of solution you have in there. So this is a common technique for determining the molecular weight of a particular solute by measuring its osmotic pressure. It's very easy to measure pressures. Pressures can be, you know, measured with great precision, and there's things called osmometers you can actually buy, like in a physical chemistry laboratory. If you ever run into this, most likely in a physical chemistry lab, you would find that they would have an osmometer. And example 216 illustrates this calculation. And I should point out a little bit about my exams is all the homework problems in the book. You know, this book's now in its 4th edition. It's been out for, geez, I don't know, 23 years, I think. So it turns out, which is kind of lucky for you guys as students, that practically every homework problem, every example that's given in the 4th edition of this book is just old exam problems. So if you're comfortable working, you know, problems like the example I just worked or this example that we're going to work, that's the kind of problems you're going to expect to find on the exam. If it's a more lengthy type problem, that involves using MATLAB or something like that, clearly I don't have any problems like that on the exam. But anything that involves calculations like what we're doing here, typically those are old exam problems. So in example 216, it says the osmotic pressure of a solution containing a macromolecule is equivalent to the pressure exerted by 8 centimeters of water. The mass concentration of the protein is 15 grams per liter. So you made up the solution of some protein, you measured the osmotic pressure. That's in these weird units of 8 centimeters of water, but you know from physics that the hydrostatic pressure is just equal to rho GH. So if you know the height of the column of water, just multiply it by its density and the gravitation acceleration, and you can calculate the pressure. So using equation 2149, we plug in all the numbers. Once again, you can see that's a beautiful rendition of the dimensional equation that I've been talking about. And when you crank it all out, you get a molecular weight of 47,400 grams per mole. Okay, so in terms of the last lecture then, we went back into chapter 2. We spent some time talking about osmotic pressure from a thermodynamic point of view, and now we can start to use that to see how it works in terms of calculating filtration across membranes and so on. So here's what we developed back in chapter 2. This is our basic Van Hoff equation. If we know, like I mentioned, if we know the concentration, we can calculate the osmotic pressure and vice versa. So we went through all of that. We also talked about how to handle multi-component systems. So we got that right there. And then sometimes it's convenient to just have an equation where all we have to do is just add up the concentrations and multiply it by a number, and we get an answer. This is kind of like a cookbook, handbook engineering kind of a thing. You don't have to worry about the units. So equation 3.3 is such of an equation. At a physiological temperature of 37 degrees, and if you have your concentrations expressed in milliosmolar, which for a non-dissociating entity would be the same as millimolar, then if you just sum up the millimolar concentrations of all the entities multiplied by 9.33, that'll give you then the osmotic pressure in millimeters of mercury. So equation 3.3 can be a quick, useful equation, but you got to remember the caveat that it's very specific to the particular units that you are using. Okay, so here's an example of how to work out the osmotic pressure for a multi-component system. And what we have here is a substance called MovaPrep. Maybe your parents have had colonoscopies, and you have to drink a large amount of fluid containing some crazy osmotic agent. There's a variety of these out there. MovaPrep is one. It's a low volume, meaning you don't have to drink a lot of fluid, but I think you end up drinking almost a couple liters of this stuff, and then you spend the rest of the night on the toilet. But the good news is for the gastroenterologist that it completely clears out your colon for the colonoscopy. So how does that all work? I mean, what causes you to have the diarrhea? Well, these things that you're drinking are just hyperosmotic. When it gets down into the colon, the body can't reabsorb all that water, and it senses a high osmotic environment relative to the osmotic environment of the body. So water flows across the colon wall, and you get this large expanding fluid volume that basically flushes you out. So on this particular case, each liter of a MovaPrep solution contains in millimoles the following components in this table. So there's something called PEG 3350, which is a polyethylene glycol. This guy does not dissociate, and I imagine the 3350 is the molecular weight of that polymer. We also have sodium chloride, sodium sulfate, potassium chloride, and sodium ascorbate. So all of these guys right here, the next four solutes are all strong electrolytes. So when they get into the water or get into the solution, the sodium chloride is going to form sodium ions and chloride ions. The sodium sulfate will form 2 sodium ions and 1 sulfate ion. Potassium chloride is going to give you a potassium ion and a chloride ion. And the sodium ascorbate, the ascorbate group stays together as a negative group, an anion, and the sodium is the cation. You're at 37 degrees C, and we want to calculate the osmotic pressure in millimeters of mercury. So this is a case where we can use that quick and dirty formula that I showed you on the previous page. We just have to figure out the concentrations of all the entities, and that's what I show next under the solution section of this. You can see I write a balance now on each of the species that I know, what each of the entities that's going to exist in the solution, and each of the solutions here, these are all the guys that are going to be present, and then I have to figure out from the dissociation calculations, which are really chemical reactions, how many millimolar concentrations I'm going to have of each of those guys. So that's outlined right here. Go through, make sure you understand how I got the numbers. But you can see we got 181 milliosmoles, or in this case milliosmolar, which would be the same as a millimolar of sodium, 59.8 of chloride, 52.8 of sulfate, 14.2 of potassium, and 29.8 of ascorbate. So according to equation 3.3, we would add up all the entities, which I show right here, because they're in the milliosmolar units, multiply that by 19.33, and as long as I'm at 37 degrees C, I can calculate my osmotic pressure, which comes out to be 7,098 millimeters of mercury, which is really high relative to the osmolarity of the fluids in your body. And because of that, like I said earlier, water diffuses into the colon and greatly expands the volume, which then helps clean out the colon. Let's talk about filtration across membranes. That's the next topic we want to look at, and we introduced the idea back in earlier in this lecture, and we have what's called Starling's equation. So we came up with Starling's equation right here. In this particular case, I wrote it for a capillary and the interstitial fluid. So if you think about the pressure inside the capillary would be P sub C. The pressure in the surrounding interstitial fluid that surrounds the capillary would be IF. Pi sub C would be the osmotic pressure in a capillary, and pi sub IF would be the osmotic pressure in the interstitial fluid. And if you have a system that you're engineering, you can still apply this equation. You just have to, switch the indices C and IF. Column A, B. Sometimes we use numbers. Region 1, region 2, and then there we go. We can work that all out. So what I want to do is illustrate an example of how to do this, and it's actually a desalination of seawater in a submarine. So let me bring up that slide. Okay, so here's the equation that we're going to use, and we're going to solve as an example problem 211. And what we have here in this problem, let me read the problem statement. Let me zoom out a little bit here so we can catch all of this. So it says here, for a submarine depth less than h, okay, so the submarine's, basically shown down here. Make a drawing. Here's the surface of the water, 1 atmosphere. Here's a bird flying. And if you think about it, you could have an osmotic membrane device that could take the seawater and make fresh water out of it. So let's say the guys inside the submarine are at 1 atmosphere. Here's some type of device. The seawater would flow in, and the salts would be retained, and you'd get fresh water. But if you're above some critical height that we call H, this device would not work, because if you had fresh water on the other side of the membrane and the depth wasn't high enough, because of osmosis, the water would go in the reverse direction and you'd actually lose water from your system. As the submarine would go deeper and deeper, it would get to some critical depth, which we're going to call H. That flow that you would have, that where you're losing your fresh water, would stop, and then as you go deeper than H, the hydrostatic pressure would be high enough now that you would actually get what's called reverse osmosis. So that's, if you've heard the term reverse osmosis, that's all reverse osmosis is it just means that the filtration flow is now in a direction opposite of osmosis. So if the submarine were below the depth H, it could conceivably take seawater, and just from the high hydrostatic pressure, you would form fresh water on the inside of the submarine. So what we want to do to explore the feasibility, we want to know at what depth, if you went below some critical depth, what is that critical depth below which you would get reverse osmosis. So that's what the nature of the problem is, and we're going to use equation 3.4, and this will illustrate, how to make a drawing, how to use equations and things of that nature to solve an engineering problem. So for a depth greater than H, fresh water flows into the vessel. Now, if you were above H, you wouldn't want to lose your fresh water, so you would just have the system turned off so that you're not making any fresh water by reverse osmosis. So we'll let PA be the local absolute pressure at the depth. So the absolute pressure at whatever depth you're at would be rho GH plus the 1 atmosphere of the air up above. Now, for there to be no flow of water across the osmotic membrane at the critical depth H, we have from our basic Starling equation written like this, and you can see that I wrote Starling's equation in a sense that the flow Q would be positive if it's going into the submarine. And the reason I do that is I know that the hydrostatic pressure outside is going to be huge relative to the internal submarine pressure. So this PA minus PB would be positive, and then this is the offset because of the osmotic pressure. So when Q is equal to 0, that becomes the critical depth, and then we would simply have that PA minus PB equals pi A minus pi B. And then what happens then is the osmotic pressure, go down here, let's take a look at PA. Remember, PA is equal to rho GH plus the 1 atmosphere up here, and PB is the pressure inside the submarine. And then we'll assume, for argument's sake, that the water that's being produced inside the submarine is pure water, so we'll just set the osmotic pressure pi B equal to 0. It's going to be very, very small relative to the osmotic pressure of seawater. So with Q equal to 0, put in PA and PB into the equation, we get the result then that rho GH, which has that critical height now, is equal to the osmotic pressure of the seawater. So at the top of the next page, we show the rest of the calculations. What we can do is the osmotic pressure of seawater based on an equivalent amount of sodium chloride is equal to this right here. As shown, it's basically seawater is like a 1 molar solution of sodium chloride. Is it 1 molar? What did the problem say? Let's flip back for a second here. Okay, yeah, I had to look at the problem statement. Yeah, in the book, the problem statement says that the equivalent osmotic pressure is as if it were a 0.5 molar sodium chloride solution. So that's what we have then here when we do the calculation up at the top. You know, we have the concentration of sodium ions, concentration of chloride ions, and since you start out with 0.5 molar sodium chloride, that splits into sodium and chloride ions, each at 0.5 molar. So that's why we have the 0.5 plus 0.5 here. Here's the temperature. Temperature is not given in the problem, but I just assumed the temperature of 20 degrees C. Here's the gas constant. So when when the local pressure is less than the osmotic pressure of seawater, fresh water is going to flow out by osmosis. When pA is greater than the osmotic pressure of seawater, we have reverse osmosis and fresh water flows. And this begins to occur then, based on our calculation, at 24 atmospheres. Therefore, rho GH is equal to 24 atmospheres, and with G equal to that value, you can go through the next set of calculations that I show right here, and you can see that the critical depth is roughly 243 meters. If you go deeper than that, then you could run a reverse osmosis system just using the local pressure, the local hydrostatic pressure of the seawater. Okay, so just a couple quick examples there that illustrate how we can use some of these calculations. This is a very important equation. We'll be using it a lot in our biotransport course as we go through. Here I've got written, remember, kind of burn this into your brain, that the flow of anything is proportional to a driving force divided by a resistance, or the driving force multiplied by a conductance. Okay, another little sidebar thing that I have over here that I want to talk about is that when you have transport across a membrane and you have solutes that freely cross the membrane, they don't contribute to the osmotic pressure. And sometimes this gets confusing to people, why we only sum up the retained solutes and we don't sum up the non-retained solutes. Now, strictly speaking, when you're talking about osmotic pressure of a solution, that osmotic pressure would be against a totally impermeable membrane. If you had a membrane that was totally impermeable to all the solutes, everybody in there except the solvent, then yeah, the osmotic pressure, you would sum over all of those guys. But when you're looking at transport across a semi-permeable membrane, where there are species that can cross the membrane, the osmotic pressure difference itself can be based strictly on the guys that are retained. And the math for this I've got kind of laid out here. Consider retained solute X right here. Okay, so we got one solute that's retained, and then we got all these other solutes in the solution. So on the A side of the membrane, the osmotic pressure would be RT times Cx on the A side plus RT times the sum of all the other guys. Okay, so this summation sign is for everybody that freely crosses the membrane, but we're going to account for them in terms of calculating, the osmotic pressure on side A. On side B, it'd be the same calculation, but now we're on the B side. Now pi A minus pi B is going to equal RT times the difference in these concentrations. And you can see these guys cancel one another out. So this shows us then that when we're talking about transport across a membrane, when we calculate the osmotic pressure difference, we only have to focus on the solutes that are retained in our calculation. Kind of a subtle fact, but it's important to understand that. Okay, the next thing we want to talk about is how do we predict the hydraulic conductance. Now, a lot of times when you're designing things, design's a process. You know, it goes from conception through preliminary designs, through the building of prototypes, and then further testing, and then finally you get to the product that you want to sell. And then as time goes on, you got to refine the product based on feedback from your customers. But in the early part of the design process, you don't have a lot of data, you don't have all the information. And as engineers, we have to make some assumptions and make some predictions about how we think the system's going to behave. Now, you know, you can easily measure the hydraulic conductance of a membrane in the laboratory. If you just take pure water and apply a pressure across a membrane, and if you measured that pressure drop across the membrane, you measured the flow rate, and you knew the surface area of the membrane, you would be calculating the hydraulic conductance of the membrane. But even going in the lab and doing a simple experiment like that, it takes time, it takes money, and sometimes you just want to be able to predict what the flow rate's going to be, and that means you need to know what the hydraulic conductance of your membrane is. And we can predict that by creating a mathematical model of the membrane itself. And then we can use that prediction to do design calculations and try to optimize the design and say, okay, this is the way we ought to go, and then build a prototype and test it and see if it actually works. Now, if you think about a membrane just is a very thin material with pores in it, and it's the fluid flows through those pores. And to an engineering approximation, we can say that the pores are cylindrical. So what you have then is a flat membrane with a large number of little cylindrical tubes through which the fluid is flowing as it crosses the membrane. Now, because of the viscosity of the fluid and the small diameter of the pores, the nature of that flow is going to be what we call laminar flow. Laminar flow just means that all the water or whatever your fluid is flowing along slowly and smoothly. Okay, it'd be like if you were in a classroom and you're all seated at your desks in columns, and I'm up in the front of the class, watching you, and you all stood up and started walking towards me. It's like soldiers marching. You got ranks and you got files, and everybody stays in their file. That would be very laminar. Okay, so you just move in a smooth flow like that. The other type of flow is turbulent flow, and that's totally chaos. If the soldiers were marching, or we went outside and you guys got up and started marching towards me, and then all of a sudden you all just started mixing laterally and moving around and just having a good time like a mob, that's what we call turbulent flow. Turbulent flow is very chaotic. And if you go in your kitchen tonight and you turn on your faucet, very low flow, you see that nice, clear, glassy stream coming out of your faucet, that would be laminar flow. If you jack the flow rate up real high, it becomes turbulent. It gets cloudy, it's crazy looking. That's turbulent flow. Well, in any case, the nature of the filtration flow through the pores of a membrane would be laminar flow. And we're going to develop an equation in Chapter 4. I'm going to show you the equation first, but this actually comes from our theoretical understanding of fluid mechanics. You might have seen it in physiology when they're talking about the circulatory system. But this equation is called the Hagen-Poiseuille equation. And it tells us what the flow rate is in a flow. And basically, the flow of anything is proportional to a driving force. So the driving force is the pressure drop along the length of the pressure difference between the inlet and the outlet of the pore divided by the length of the pore. Okay, so the driving force, and then everything else here is what we call the resistance. This is due to the resistance. And you can see here, this pi right here in Hagen-Poiseuille equation, that's the 3.14 pi. That's not osmotic pressure. R is the radius of the pore, and it's to the 4th power. So you can see that the radius of the pore has a very strong effect, for a given pressure drop on the flow. And your body makes use of that. All your arterioles and stuff in your body have smooth muscle, and the body's able to regulate flow very precisely with minute changes in the radius of the arterioles. In the denominator, we have a symbol here we call mu. Looks like a U, but it's the Greek symbol mu. That's the viscosity of a fluid. So the viscosity of a fluid is the flow resistance of a fluid. A more viscous fluid is harder to move through a tube than a less viscous flow. So pancake syrup's a lot more viscous than, say, water. And L is the length of the pore. So this whole term, everything other than the driving force, the pressure difference, would be the resistance to the flow. So this tells us what the flow is through one pore of a membrane, provided that we know the pressure drop across the membrane, which in our case, because of osmotic effects, would be the effective pressure drop. We'd have to know the radius of the pores, the thickness of the membrane, and the viscosity. These are all engineering variables. If you're involved in a design of something, you're going to know those quantities. So what we do then is we just use the Hagen-Poiseuille equation and multiply it by the number of pores that we have, and that would in our membrane, and that would tell us what the total flow is across the membrane. So that's what's illustrated on the next page here. You can see we got then that the filtration flow across the membrane, according to equation 3.4, would be LP times the surface area of the membrane times the effective pressure drop. That's our basic filtration flow equation. What we're trying to do is come up with a theoretical model that we could use to predict hydraulic conductance. And using the Hagen-Poiseuille equation, we would know then if N were the number of pores in our membrane, then if we multiplied the number of pores by the flow rate per pore based on that effective pressure drop, we should be able to extract out from that an equation for the hydraulic conductance. So this illustrates how engineers think about problems and how we try to create mathematical understandings of a problem so that we have a deeper understanding, with the goal then that we can use these equations to interpret data as well as use them for design. Now it's important to recognize that the thickness of the membrane, which is given by L bar, okay, so L bar in this case is the thickness of the membrane, which tends to be greater than or equal to the actual, or it turns out that the actual pore length is greater than or equal to the membrane thickness. What happens is the pores in a membrane can be twisty, they can be tortuous. So what we do then is we multiply the thickness of the membrane, which is L bar, by another parameter called tau, which is the tortuosity of the membrane. So the tortuosity might be 1.5. Okay, it's not the straight line distance, which would be L bar, the thickness of the membrane, but the pore length tends to be a little bit longer. Okay, so the total cross-sectional area of the pores is equal to N times pi r squared. Okay, so N right here is equal to the total cross-sectional area of the pore, A sub p. So what we can do then is, because pi r squared would be the cross-sectional area of one pore, multiply it by the number of pores, that's your cross-sectional area of all the pores. So we can use this equation right here and solve for N in terms of the cross-sectional area of the pores. So you put that expression in for N, and you get equation 3.7. Notice now that we have and solve for LP, notice that the effective pressures cancel out. So, in our model, this model is independent of what the pressures is, which is kind of cool. So that's gone. And then we end up with this ratio of AP over S, the pore cross-sectional area divided by the total membrane surface area. This would be the surface area of the openings divided by the total membrane surface area. That ratio is called the porosity of the membrane. When you buy membranes or you make membranes, you're going to make those membranes with a specific porosity, epsilon. That becomes a degree of freedom. That's part of your design process. You're saying, hey, I want my membranes to have a porosity of 40% or 25%. So you can see then that what happens now with AP over S being epsilon, we now have an equation 3.7, which is an equation by which we can predict hydraulic conductance if we know the radius of our pores in our membrane, if we know the porosity, if we know our membrane thickness, if we know the viscosity of the fluid. We can now use that equation to predict hydraulic conductance. So let me illustrate how to use this in this example here. Let's take a look at this here. It says calculate the filtration flow rate of a pure fluid across a 100 square meter membrane. Assume the viscosity of the fluid is 1.8 centipoise. Now that's just a unit on viscosity. When we get into chapter 4, we'll talk about where that comes from. Just for example though, the viscosity of water at 68 degrees, I think it is about 1 centipoise. Okay, so this fluid's a little more viscous than water. The porosity of the membrane is given as 40%, and the thickness of the membrane is 500 microns. The pores run straight through the membrane. When you read these problems, when it says the pores run straight through, that would mean the tortuosity of that membrane pore is equal to 1. And they have a radius of 0.225 microns. The pressure drop applied across the membrane is 75 psi. And then I show some units conversions here, and you got table 1.1 from chapter 1. Okay, so what we want to find here is we want to find the filtration flow rate across this membrane. So we're going to have to use equations 3.4 and 3.7. 3.7 we use in order to estimate the hydraulic conductance. Since there are no retained solutes in this problem, there are no osmotic effects, and the effective pressure drop across the membrane is just equal to the applied pressure drop of 75 psi. From the information about the membrane, we first calculate the value of the hydraulic conductance, and I'm showing the calculations below which lead to that. So the porosity is given as 0.4, the radius is equal to 0.225 microns. Notice I convert that into centimeters. I find it very convenient to work with centimeters. Okay, once in a while meters, but it's usually better to get out of units like microns and stuff before you get into your calculations, just so you can save space in your dimensional equation. Likewise, I convert the thickness of the membrane into centimeters. The centipoise, that's an oddball English type unit. The best units for viscosity are Pascal seconds. Okay, so we can convert centipoise into Pascal seconds by noting that 1 centipoise I show up here is equal to 0.001 Pascal seconds. The nice thing about viscosity is Pascal seconds. If you put your pressure drop in pascals, usually the pascals will easily cancel out. If you don't do that, you can end up with a unit's nightmare. It's not the end of the world, but things just become a little more complicated. Notice I convert the oddball pressure drop of 75 psi, I convert that into pascals as well. So now I got everything in pretty compatible units. So at the top of the next page, we calculate the rest of the information in the problem. You can see here now by equation 3.7 we're calculating the hydraulic conductance, and we end up with units of 2.813 times 10 to the minus 7th centimeters per Pascal second. Okay, that's our hydraulic conductance. Now we go into equation 3.4, multiply the LP by the surface area, multiply by the applied pressure, and we get a filtration rate of 14.5 cubic centimeters per second. Would be the filtration flow across that 10 by 10 centimeter membrane. So a 10 by 10 centimeter membrane is roughly 4 inches by 4 inches. And when you get a number like this, think about what that number means. You know, in a minute, 60 seconds, you're going to put out almost a liter of fluid. Would that make sense in 1 minute to filter 1 liter of fluid across? It seems pretty reasonable. Many times people will make mistakes with units, and they might end up with 14.54 times 10 to the 6. Okay, so you immediately got to look at your answer. You know, don't be so jaded by your engineering that you just get lazy and just write whatever number down just so you can finish the problem and move on to the next one. You got to critically look at your answers and ask yourself, does this number make sense? If it doesn't seem to make sense, just by some analogy like what I just told you about, that's a good sign then to go back, and you probably made a mistake with your units. Now, up until this point, we've been talking about circular pores. What if you had rectangular pores in your membrane? Okay, there's techniques where people can make, they can etch in, like in silicon wafers and stuff, they can etch in rectangular pores. So imagine now we've got a rectangular pore. Here's the cross section. This is the length of the pore. Here's the filtration flow through a single membrane. Imagine that the slit pore here is drawn, has a thickness of 2H. So H would be the half thickness of the slit, W would be its width, and L is the pore length. Now in problem 425 in chapter 4, sometimes I assign this problem, you can show there's an equivalent version of the Hagen-Poiseuille equation for flow in a rectangular slit, and that flow rate is given by equation 3.8. So now this would be the Hagen-Poiseuille equivalent flow equation for flow in a slit. So what you do, again, just like what we did with the cylindrical pore, is we say, okay, equation 3.4, Starling's equation, has to now equal n times our flow rate through one of these rectangular pores. And you go through the same argument again, calculate the pore area is going to be 2H times W. That's the pore cross-sectional area times N is the number of pores. And you can end up with equation 310, which would be the hydraulic equation, or the hydraulic conductance, if you have rectangular pores in your membrane. And it's kind of interesting to compare these two results, the hydraulic conductance given by equation 3.7 for a cylindrical pore and this one for a rectangular pore. So if you say, okay, if they have the same, comparing these, with a slit pore half thickness equal to the cylindrical radius. So, if you were trying to evaluate, should I go with cylindrical pores versus rectangular pores, and you said, okay, let's make the cylindrical pore radius the same as the half thickness of the slit. And then if you had everything else the same pressure drops and everything, and you set up the problem, you would find then, everything else being the same, that the rectangular pore has a hydraulic conductance 2.67 times that of the cylindrical pore. So it's kind of interesting from the physics of this problem that the rectangular pores have a much higher hydraulic conductance, which would give you a higher filtration flow. And this explains why we oftentimes see rectangular openings in many filtration situations. In nature, we see this in the capillary membrane with the slit pores of in the intracellular cleft. Certain baleen, certain types of whales have these baleen plates that they use to filter the ocean water. You've probably seen those. They open their mouths and they got these big rectangular openings where they're filtering the seawater and capturing the little animals that live in the seawater. We also see this in storm sewer drain covers. Most storm sewer drain covers have rectangular openings. If you take a walk, look at them sometimes. Also, colanders in the kitchen, the better ones, the ones that drain really fast, will have rectangular openings rather than circular openings. So yeah, that's the hydraulic conductance. Now we figured out how we can understand mathematically what's going on with that. And this equation makes sense too, because it tells us that if you make the fluid more viscous, that's going to decrease the hydraulic conductance, which is going to decrease the filtration flow. If you increase the thickness of the membrane, you get the same effect. If you increase the porosity, that increases the flow. Notice if you increase the size of the openings, it's to the square. So if you double the thickness or the radius of the pores, you're going to effectively increase the flow by a factor of 4. These are all things that, through intuition alone, you probably would never be able to come up with the right relationships between all these variables, but by doing some simple mathematical modeling and coming up with representations of what's happening, we can come up with useful equations. So why don't we stop here, and we'll get back into this stuff on Wednesday, probably finish up Chapter 3 on Wednesday and start Chapter 4 on fluid mechanics.